All right. So, welcome to ENGR 210, the review session 10, I believe. Today is 10/13/25. And today we are kind of continuing the trend of it's a lot of the same stuff, but with complex numbers now. Um, however, like there is like actually one new thing this week. Uh, yeah. Okay, yeah. Yeah. So today we're going to go over op amps again. I'm not really going to go over them. I'm just going to do practice problems because it's again exactly the same thing. And then we also have complex power, which is a confusing topic, which like I remember last semester when we got to this section, I had to like re-explain it to myself as well. So there's that, but it was on the homework, so more than likely it'll be on the quiz. So it's good to understand it. Let me pull back up the homework here so I actually know what I'm talking about. Uh, yeah. So, okay. So basically, I'll give my best attempt to go over complex power. So, just like how when we go into the frequency domain, we represent voltages as phasors and we represent currents as phasors, right? Similarly, we have what is called complex power, which we represent with S. And we represent this, again, in a phasor form. And this S, so this is the phasor form. However, of course, complex numbers also have their A plus JB form. And for complex power, so this is complex power, it has two components. It has the average power and the reactance. So this is the average power, and this is the reactive power. Actually, yeah, it's reactive power, not reactance. My bad. Reactive power. So the reactive power has the imaginary part. The average power is the real part. So if you wanted to represent this in the complex plane, you could say that if I have some vector or some complex number S, it has this amount of complex power and this amount of real power, right? So by that logic, there's a bunch of different like is like just that's that. That's pretty straightforward. Now, how do we relate this complex power to our complex voltage or to our phasor voltage and phasor current? Okay, this is the other equation that's important. So S here is going to be equal to 1/2 V times the conjugate of I. Very important that it's the conjugate. I forget exactly why, but that is very important. Otherwise, your numbers will be wrong. So if you need to remember one equation, I think this is like the most important one, and then maybe also this. And yeah, um, that's a big thing. Just as a reminder, if I equals uh right. So if I equals a plus jb or like ae to the j theta, then I conjugate is going to be equal to a minus jb, which is the same, I think, as ae to the no, it's not the same. I don't know if you can just relate the angle like that. I don't think it's negative theta. Is it? Yeah, yeah, it is. Okay, yeah. So you gotta when you're doing the power, so like this is saying if I had like some complex voltage source and I don't know, there was like a resistor and a capacitor, and it asked me what is the power here, you would find, okay, I have some complex current here, and I do a voltage divider, and I say, okay, I have some complex voltage here. You multiply 1/2 times this times the conjugate of that, and you would get S. So that's like why we would need to be thinking about this. And if you try, so part of the reason this is weird is because it's like weird to think about what complex power means. What you can try to think about is, as we said before, it's equal to the power average plus the reactive power. So in a circuit, right, the power average is the real power. So this is like equal to this is like the stuff that's actually getting dissipated in your resistors. So this is like, you can think of this as the power with that's kind of associated with resistors, and this is the power that's inductors and capacitors. Um, if you think about it, right, inductors and capacitors don't actually dissipate any power. They just kind of like store it and then release it. So when they say average power, what it's saying is like this is the power that will actually get turned into heat, whereas this is the power that's just kind of like being passed back and forth between your inductors and your capacitors, right? So like she probably, I hope she talked about that more in depth in class, but like there is, so this is like the real there's the reason it's like the real component because it's the stuff that's actually real. I'm I really don't think you need to know much of this for class, but it's like good to kind of understand it. You're engineers, you should understand things. Okay, then the other couple things are okay, some other equations here, yeah. What is phi? Okay. Power factor, also written as PF, is just you can write it in a couple ways. It's either P average over the magnitude of S. So you're always going to have you should always have a real average power because you can't like, at least for like a resistor or something, you're always going to have a real average power. Um, so it's that which by trigonometry is equivalent to like S times the cosine of the angle of S, where that's like the inverse tangent of Q over P av, which is the same as VRMS times IRMS times the sine of 5V. Oh no, no, I got distracted, sorry. It's I'm a fool. It's where was I? Let me go back. Okay, the two important ways to understand it is the ratio of the average power to the complex power. It's also just the cosine of the angle of the complex power, which is the same as the cosine of the difference between the phase of the voltage and the phase of the current. And so power factor, that's like you can think of it as like how much of the complex power going into something is like actually being dissipated as heat. And yeah, again, this is kind of like the most complicated topic in the class in my opinion. So if it's complicated, it is complicated. Maybe look up a YouTube video about it. Um, I personally haven't really had to do anything with this in the rest of my education at Case so far, but I'm sure if you end up getting into like power systems, like the power grid, it would matter. So if that's something you're interested in, then maybe look at it more. Okay, the one other thing is for max power transfer. Let's say we have some source voltage and it has some associated source impedance, right? Or you can think of this as like your VTH and your ZTH, whatever, right? You have some circuit and it has something that it can be modeled like this. If we want to attach a load, a ZL, and have it dissipate the most average power, so for maximum power transfer, ZL should be equal to the conjugate of ZS or ZTH, I'll say. What this does is it makes it so that your P average, if you do the math, you end up getting 1/8 times that VTH squared over RL, where RL is just, so this is going to be equal to RL plus JXL. So it's just the real component of that impedance. And another thing, P average is like, in this case, it's always going to be real and positive. So if you have a question asking for maximum power transfer, you have to kind of just find the equivalent impedance of the circuit, take its conjugate, uh, that is the equivalent ZL, and then when you're actually finding the real average power, you take the real component of your impedance and plug it into this equation. Cool. Cool. I'll like do one or two complex power questions, but it's a confusing topic to say the least. Hopefully, you all have been paying thorough attention in class, and this is a nice review for you. So, yeah. However, because I want to, I'm going to, oh, actually, this works. Okay, I'm going to do an op amp question that kind of mixes the two. So, with op amps, just like I've been saying the past 2 weeks, it's like everything's exactly the same. It's just now you have complex numbers. So, hopefully, you'll see that to be pretty straightforward and true. So we got this. Uh, okay, so this is asking us to find the complex power of ZL, right? So this means we have to find V bar, so it's going to be 1/2 V bar times I bar conjugate, where V bar equals VO, of course, and then I bar is like that. So we solve this like any other op amp question. We have our VP and our VN. VP equals VN equals 0. In this case, pretty nice and straightforward. And then at VN, let's do a thing. We're gonna go, okay, we got VN minus 2 over 200 minus J500 plus VN minus VO over 2400 equals 0. And remember that Vn and Vn is 0, so we can rewrite this as VO over 2400 equals -2 over 200 minus J500. And then we can multiply by 2400 and we get -4800 over 200 minus J500, I believe. Yeah. And I'm actually going to write this in a slightly different way so I can make a point. So it's going to be 2 times negative 2400. The reason I'm writing it like this is because if you remember your like most basic op amp circuit you learned, it was something like this, right? Where you had this, you had a resistor here, and you had a resistor here, and then you had your input, and this is your output. This circuit here is exactly the same as this circuit here, right? This is our input. This resistor has become these two things, and this resistor has become these two things. And if we remember, the gain on this one, which was V out over V in, was negative R2 over R1, where this is R2 and R1. And in this case, if we look, wow, doing this math has gotten us to exactly the same place, where we have R2 and we have R1. So just goes to show everything still works exactly the same, right? So this is our V out. Anyway. However, since it is actually asking us to do math on this V out, we should simplify it a bit. So this is going to be something, and actually I said I'm going to simplify it a bit, but I'm just going to put it in my calculator and let it do it for me. So let's see. And I'm also going to have it put it into phasor form because it's so kind. Actually, I'll have it in both just because I can. So this is 2 times negative 2400 over parentheses 200 minus j 500. This gets you a very not nice to look at number, which is negative 3.31 minus j 8.28. It has a lot more decimal places than that, but it doesn't matter. And now, yeah. Okay. And now we're going to say, okay, now that we have V out, this is the same as V bar for that ZL, right? And now we want to find SL. So one thing here is you can note that in this equation we had in the top here, right? We know that V still equals IZ, right? So we can plug in, since just like with when we had P equals IV from real time domain stuff, right? This could also be written as I squared R or V squared over R. We can do a similar thing here where after doing a tiny bit of math, so we say 1/2 V naught times, or not V naught, 1/2 V bar over Z conjugate, and then just complex number stuff. Like if I have some complex number times the conjugate, it's equal to the absolute value squared. That's just a thing. You can prove it for yourself if you want. But we end up getting that SL is also equal to V naught squared over ZL conjugate. So I'm going to use this equation. However, if you wanted to, you could also just find I bar normally. But, this equation, it's a nice way to not have to find I bar at all, you know? So anyway, we're here. We know that SL equals 1/2 of the voltage there squared. So this is the V bar squared over the conjugate of ZL. And in this case, what is the magnitude of V naught squared? So that's going to be just, well, the magnitude, right, is going to be A squared plus B squared, and then you square it, so it's just A squared plus B squared. So it's going to be I'll write it out here. It's going to be 3.31 squared plus 8.28 squared, and then over the conjugate of our ZL, so that's going to be 100 minus J1000, right? And if I take this lovely number and plug it into my calculator, let's see what I get. We're going to get 0.5 times, just think we have, yeah, you can just take the absolute number of some, or absolute value of stuff on your calculator. That's nice. That squared divided by 1000 minus J1000, and we get, this doesn't feel right, but I guess it might be. Let me think. Um, mm, mm. Oh, yeah, okay, sure. That actually, yeah. So this gets us 0.0198 or 0.199 plus J 0.199, which you can kind of simplify down, or that's not actually a squiggly line, it's an exact equal line. If we turn this into if we turn this into the other form of imaginary numbers, right, this will end up being 0.028 e to the j 45 degrees volts amps. Oh yeah, the unit for complex power is volts times amps. You don't say power for some reason. You just say volts amps. I'm not exactly sure why, but yeah. Hold up, my neighbor is shouting something. I don't know what he just said. Whatever. Okay. Anyway, so that's that. So this is saying that that's the complex power going through there. So that's how you'd answer that kind of question. Very cool. Let's see. Okay, that was an op-amp question. Now I'll do another power question. So, doo-doo-doo. Okay, so it's saying find the power factor. That's a P, trust me. Power factor of the 2 amp source. So if we remember, the power factor is you can either think of it as the cosine of the phase of the voltage minus the phase of the current. And it's also just like the phase of, or it's the cosine of the phase of the complex power, right? And it's also the power average over the magnitude of the complex power. All these things are the same. So we have to find one of these. In this case, it will likely be easiest to just find this one. Why? Well, we already know what the current through the current source is, right? Because it's a current source that's telling us the current. And in this case, this is just 2 amps, which is really in the phasor domain, it's 2 e to the j0, right? So that's telling us that the phase of the current is 0. So in this case, that means the power factor will actually be cosine of just the voltage because it's minus 0, right? So we just need to find the phase of the voltage here. So in that case, we just need to find, okay, what is the voltage across this current source? To do that, I will do like a single node voltage equation. So we got V1 and we got ground at the bottom. Okay, and now at V1, what is our equation? We got, okay, V1 minus 0 over J5 plus V1 minus 0 over negative J10 plus V1 minus 0 over 20 minus 2 amps equals 0. And I'll go through how I would do this in my calculator because I don't want to do the math on written out because I will mess it up if I try to. So it would be V1 times 1 over J5 plus 1 over negative J10 plus 1 over 20 equals 2. And then you can just divide 2 by that whole expression, which I will do for you right now. So if I do 2 divided by, in fraction form, 1 over 5i in my calculator plus, 1 over negative j10 plus 1 over 20, we get V1 equals 8 plus 16j, j16. Which is a pretty nice number. That tells me that I probably did it right, I think. Let's see. Is that too good to be true? No, that feels right. Which, if we then take this, it can also equal if I switch the mode on my calculator. Or if you wanted to do it right, remember A equals this and theta equals 16 over 8. If we do that, we're going to end up getting 17.89 e to the j 63.43 volts. Now, remember, we were trying to find the power factor originally. So now we've found the voltage across the current source, and we already have the phase of the current. Now we just need the phase of the voltage. So the phase of the voltage, of course, is just it's that. We found it. It's that number. So in this case, if we want this minus this, we already found both of these now, so it's cosine of 63.43 degrees minus 0 degrees. And this, if we do that, is going to be cosine of 63.43. Make sure you're in degree mode if you're doing this on your calculator. And it's about 0.447. So cool. We did it. And this is saying that, like, I guess if you want this in words, it's like 44.7% of the power of the complex power is actually is actually being dissipated like as heat, I suppose. Yeah. So that's saying that like the rest of it, so that's like the amount that's like going through this resistor pretty much. The rest of it is basically being tossed back and forth by these components and like then going into here. But the reason that it's imaginary power, the reason that we don't call it the average power is because it's like going up and down, up and down, up and down here. The average power is the stuff that's actually being dissipated. Everything else is kind of going up and down on top of it. So you can imagine that like if this is our average power and we're looking at like the current going in to our load, right? You have your average power there, and then maybe on top of that, you have this, and this part would be like represented somewhat by that like imaginary power. Yeah, cool. But the key part of this, for this class at least, is know know that equation and know what these things are, and then solve your circuit. Very cool. Okay, I'll do this one too. Should probably do more op-amp questions because there was a lot of op-amp questions on the homework. So I assume you'll probably have an op-amp question on this quiz as well. Let's see. This one's similarly chill. Let's do this. Um, yeah, I'll do that. So we got that's the wrong thing. Hmm. Okay. So let's say we have a circuit like this, and it says find V out of T. So first thing we do here, we start in time domain. We have to transfer everything to the frequency domain. So for the voltage source, very straightforward. It's just going to be 10 because there's no phase on here, right? This is plus 0 degrees. So our V bar is just 10 on this thing. So I'll write that here. 10. This stays as 10 ohms as well. For our capacitor, ZC equals negative J over omega C, which in this case is going to be negative J times 1 over 1000 times 500 times 10 to the negative 6. I probably could do that if I thought about it, but I won't mess it up if I put it in my calculator. So let's see what we get. And it's negative 2, negative J2. Okay, so here we got negative J2, and that's the only thing we have to care about. So now we just solve it like a normal op-amp problem. So first we have to find what VP is. What's VP? Let's find out. VP, as you can hopefully see, this is just a loop. There's no current going here, so you can think of this as a voltage divider. The voltage divider is going to be uh, our input 10 times negative J2 over 10 minus J2, which in this case, I'll go through the math for this because it's not that bad, and surely I can do this in my head or on paper here. So negative J20 over 10 minus J2. If we multiply this by 10 plus J2, actually we can divide top and bottom by 2. So it's negative J10 over 5 minus J. Multiply it by 5 plus J over 5 plus J. You get negative J50 plus 10 over 26. That feels, it's a weird number. Oh no, I'm doing it right. Okay. And this is about 0.385 minus J 1.923. So that's VP, right? And so then that is also Vn. Now, at Vn, we do a node equation, and so it's Vn minus 0 over 5 plus Vn minus 50. Nope, fuck. Vn minus V out over 50 equals 0. And now this is a scenario where I'm not going to plug in this number immediately because that will make my algebra much harder. I'm going to solve for V out in terms of Vn, and then once I'm done with that, I'll plug in Vn, right? So if we do that, we're going to get Vn times 1/5 plus, or actually I'll leave V out on this side. Actually, that doesn't make as much sense in my head, so I will do what I was doing originally. Vn times 1/5 plus 1/50th equals V out times one, or V out over 50, I suppose, right? And then if we do this, actually, that's just a stupid way of doing it. Just multiply both sides by 50. Yeah. So we get 10 Vn plus Vn minus V out equals 0. V out equals 11 Vn, and then we plug in 11, we plug in Vn. V out then is going to be 11 times 0.385 minus J 1.923, and that gets us V out is 4.235 minus J 2 point or 21.153. So we found this, we found V out. However, this is the frequency domain, right? And it was asking it in the time domain, right? So we have to go back to the time domain. To do that, we first have to turn this back into a phasor. So A is going to be equal to 4.235 squared plus 21.153 squared. And the theta is the square root, nope, is the tangent inverse of the imaginary part over the real part. Dot, dot, dot. We end up getting that V out is also equal to 21.58 e to the negative j 78.68 degrees volts. And now this we can easily turn back into the time domain, right? So this is going to be V out of t is equal to 21.58 cosine. Remember what our original thing was up here, our omega. Boom, we bring it down here. It's 1000 t, and our phase was negative 78.68 degrees volts. And that is our final answer. So that's that's that. Pretty cool. Wow. Yay. All right. Yeah. So it's like kind of amplifying the signal and shifting it a bit to the side. That's your answer. Okay. I still got so much time. That's crazy. Okay. I guess I'll keep doing stuff. Um, mhm. Yeah, I'll do this, sure. So, okay, and it's asking us to find P av of the inductor and the reactive power, which was the Q of the inductor. So remember the complex power is equal to 1/2 V bar I bar conjugate, which is equal to P av plus JQ. So it's asking us to find this Q and this P average for the inductor. So let's do that. So to find this, right, we need to find the current and we need to find the voltage. So let's start by finding the voltage because I think node voltage is straightforward, and this looks like it has a pretty straightforward spot to do a node voltage equation, right? Right there. So if we look at this and we say, okay, I got my V1 and I got my ground down here, then if we wanted to find the voltage across this inductor, right, it would just be the voltage of the inductor would be 24 minus V1, right? So if we find V1, then we're good there. So let's call this VL. We'll just leave that there. So at V1, we're going to have V1 minus 24 over J3 plus V1 minus 0 over 2 plus V1 minus 0 over negative J6 equals 0. If we multiply everything by negative J6, or just by J6, I suppose, we're going to get 2V1 minus, what is this, times 2, so minus, shit. Oh yeah, we're saying, yeah, minus 48. Yeah, I'm thinking too much. Plus, here it's J6 over 2, so it's 3JV1 plus V1. No, minus V1, true. Minus V1 equals 0. That was times just J6. Then if we combine our like terms and such, we get 48 and V1 times 1 plus J3. I'm doing it right. Okay, let's go. And then V1 equals 48 over 1 plus J3. Multiply it by the conjugate to get rid of the thing in the denominator. And we get 48 minus what's 48 times 3, man? It's been too long since I've had to do that. It's 144. Yes. Minus J 144 over 3 squared plus 1 squared is 10. And surely I can divide by 10. It's 4.8 minus J 14.4. Okay, so we found V1. Cool. Now we remember VL, which we needed to find here, right? Because it's in the complex power thing, is going to be equal to 24 minus V1, which we just found, is 4.8 minus J 14.4. The real parts subtract, and the sign of that thing is going to flip. So we get 19.2 plus J 14.4. Wow. Okay, now let's see what are we doing now. Now we need to find the current flowing through it, right? And so there's a couple ways we could do that. Let's see. Yeah, so we can either I'll go over like a couple methods you could pick. So we have the voltage here, right? And so we can do the same thing we did in the previous question here, right? Or we can use this equation because if we know there's a voltage difference across this, we know that uh, if V equals IZ, then I equals V over Z. So we can just directly determine the current there. Or if you wanted to, you could like find the current here and the current here, and then you know that this plus this has to equal that. And you can find this by just doing V1 over 2 plus V1 over negative J6. Like there's many ways you could do it. However, the most straightforward way is definitely just we have VL and we have the resistor. So, or the equivalent resistor. So we can just use that equation we had earlier. And I'll go through that derivation one more time just so that you guys know what I'm saying. So this is the key equation you have to remember, right? And this, if we do some algebraic rearranging, we get that, right? Which is equal to that. Ooh. Okay. So we're here, right? We have ZL. So in this case, the Z is going to be just like whatever the equivalent impedance of the thing we're looking at is, right? In this case, it's just an inductor. So ZL originally is just J3. So ZL conjugate is going to be negative J3, right? And then we just found the voltage. So the magnitude of the voltage then is going to be 19.2 squared plus 14.4 squared, which ends up being, let's see if they have that here. It ends up being, oh, just like, really? Just 24? Oh, I think it's just 24. That's nice. Yeah, so it's 24. And then 24 squared over doo doo doo. Yeah, okay. So then we plug everything in here. You get 1/2 of 24 squared over negative J3. And let me plug that into the calculator. 0.5 times 24 squared divided by open parenthesis negative J3. And we get 96, uh, just J96, which is also 96 e to the J90, right? So this is our answer, right? So now this is our S overall. So we can rewrite this as a 0 plus J96, right? And then if we're remembering that S equals power average plus J reactive power, if we correlate this with this, right, then we have our final answer that P average is 0 and the reactance is going to be 96. And then this is the units. It's like volts, amps, reactive. So that's, make sure you know that, I guess. But it would be 0 volt amps and 96 volts amp reactive. Just as a gut check, thinking back to what all this means, this is saying that, okay, in an inductor, which is just a loop of wire, there's no resistance, right? It's saying that no real power gets dissipated. This makes sense. There's no power getting turned into heat in an inductor. It's just being stored in the magnetic field or being released from the magnetic field back as current. So that checks out. And then the fact that since it is like has an imaginary resistance, that it would have an imaginary power, like, yeah, it checks out. So good gut check, make sure your numbers make sense. Think about things like that. So that would be that. Wow. Smiley face. I don't know. Okay. I still got 15 minutes. I'll do like one or two more questions. Let's see. I'll do this. Okay. So this is saying find ZL for max power transfer and what the P average of that is. And I should label the rest of these as well. So to do this, as I said before, you kind of just want to do the Thevenin equivalent to find the equivalent or like the Thevenin impedance and then find the power based off that. So let me refer back to that. So I'll copy that equation over. Where were we? Is it this? Nope. It was on this page. Yeah. 1/8 VTH squared over RL. So let me write that. We know that the average power is 1/8 VTH magnitude squared over RL, where RL is the real component of ZL, right? So that means we need to find ZL and we need to find VTH. So let's do that. Oh, and we know that ZL is going to be ZTH conjugate. So If we call this A and B, now we just need to find the Thevenin equivalent. So for now, we'll pretend like this is an open circuit here, right? So we want to find our VA and VB, or we want to find our VAB. I will think of this as having this point at the bottom here. Let me connect that so it's clear. Okay. I'll think of this point at the bottom as 0 volts so that we know that VB equals 0. Then if we called this, I don't know, V1, we know that VA equals V1 plus 12, right? Because we have a 12-volt source here. So then if we want to find VAB, it's going to be V1 plus 12 minus 0. So we just have to find V1, pretty much, right? So let's find V1. At V1, we got, okay, V1 minus, ooh, but look, it's upside down, so it's negative 24 volts, right? And it's actually, oh, it's weird. Okay, so this is actually much easier to do as a voltage divider. Never mind, we're going to do a voltage divider. Because if you look, right, since this is open, for calculating the Thevenin equivalent voltage, this is open, so there's no current going this way and there's no current going this way. So all the current is flowing in this loop here. So we can look at this and say, okay, it's flowing here. We're just looking at this. There's 3 resistors and 1 voltage source. It's just a voltage divider. So it's going to be V1, because remember V1, I've decided that this at the bottom here is 0 volts. So it like the references work out fine, right? So V1 is going to be equal to negative 24 volts to keep the polarities right, times J2 over J2, or negative J2 plus J2 plus 2. This, the J2s on the bottom cancel, and you end up with negative 24J, I think. It's pretty pretty straightforward, I think. There. Let me see. Yeah. Yeah. Then if we want to find VAB, right? Remember VAB, as we wrote up here, VAB is going to be equal to 12 minus 24J. Cool. So we found 1/2 of our thing. That's VTH. Now if we want to find ZTH, we think of this where we short our voltage sources and we keep the circuit the same. And we say, okay, what is the equivalent impedance looking into the circuit this way? We have negative J2, J2, and 2. Okay, well, we have, okay, if I go in A, then I can either go this way or this way. So we have these 2 things in parallel with this. So we have, forgive, oh my God, that's, okay. So we have negative J2 plus 2 for that left path in parallel with J2. And this we can write as, what's it going to be? Can either write it as negative J2 plus 2 times J2 over negative J2 plus J2 plus 2 plus J2. Actually, yeah, that's the best way to do it because these will cancel again. Very fun. Usually, with questions like this, if it was written well, they'll make the math easy if you're doing it the right way. So this would end up evaluating to 4 minus 4 plus J4 over 2. Am I doing this? This feels, yes, yes, this is right. And then this is 2 plus J2. And so this is our ZTH. This is all of the impedances combined there. Very fun. Okay. Now, however, it's asking us for the ZL. Okay, wait. So actually, just a quick aside, I will write out what this looks like now with our simplification. Actually, I'll leave that out. So we have our ZL, which is equal to 2 plus J2 ohms, and our VTH, which is 12 minus 24J volts.
Oh, is ZL not supposed to be
Oh,
the conjugate of ZTH instead?
yeah. No, good catch. I wrote the wrong thing here. This is ETH.
Okay.
This is ETH, and then yeah. So now ZL is going to be ZTH conjugate, and that's going to be 2 minus J2, right? Good catch. So this was our A and B. Okay, so we have everything now. Now we just need to plug it all in back to our original power equation. So first off, we've answered the first section of the question, right? We found ZL. So I'll write that first, right? ZL equals 2 minus J2 ohms for maximum power transfer. And then for the second part of this, okay, we want to use that power average equation. It's this over RL. And here we get 1/8 or 1/8 times, okay, what's the magnitude of VTH squared? So that's going to be equal to, okay, it's this. If the magnitude of VTH squared is going to be 12 squared plus 24 squared, which is 720. And then that over RL, we'll write some other arrows. That's over 2. So we have 720 divided by 2 divided by 8, and we get 45 watts. Because power average is like real power, we can say that in watts. So that would be our answer for that. Okay, so we've gotten everything. Okay, so taking a step back, one thing I want to emphasize is that for questions that are asking for the max power transfer, the goal of that from like a broader perspective is to maximize the P average, right? You're not maximizing S, you're maximizing the P average. Um, when you do that, you should always end up with a P average with this equation that is real and positive. So if you get something that is not real and positive for P average, which if we recall, S is equal to P average plus JQ, right? So if you use this equation and you end up with something that is not real, then you did it wrong. So make sure you're getting something that is real and positive for for the P average max. Okay. Wanted to say that because people will just try to like use this equation and then accidentally plug in like ZL here and then it's wrong because you get an imaginary number here. Yeah, things like that. So basically this is set up in a way if you were to solve this is the kind of thing where like if I were to solve this, this is the equation I get, or this is the expression I end up getting here. Because when you have the ZL be the conjugate of ZTH, what happens is that, okay, if I add these two in series, this and this are going to cancel, right? Because you just add them together, right? You have 2 plus J2 plus 2 minus J2, and you end up just getting 4, right? Which is a real number. So that's why it has the maximum power transfer. Hopefully that's makes somewhat sense. Yeah. Okay. I have time to do like one more op amp questions. Let me find one of those. Yeah. Okay, this is a another pretty straightforward one, but it's still like bringing together a lot of the stuff that we've talked about. Okay, so it's asking for the complex power of ZL and the power factor of ZL. If we remember, this is 1/2, and if we use that equation that we found earlier, it's v squared over zl conjugate, and this is going to be the cosine of that, I suppose. Yeah, so cosine of phi s, I think. Let me make sure I'm, yeah. So we really just need to find v, we need to find this. That's the only thing we don't have already, right? So we need to find v out. So first off, we have to just find v out, which means you just have to do the op amp question. I didn't fill in the numbers, so I'll do that now. Okay, but now it's just a normal op amp question. Vp equals Vn equals 0 in this case, because P is tied directly to ground. So then at Vn, we have Vn minus 2 over 5 minus J2, right, because of that capacitor, plus Vn minus V out over 20 equals 0. If we look at this, this is again just that inverting amplifier we saw before, right? It has the resistor on top going to V out and the resistor on this side, and then a voltage source here, which is 2. In this case, remember it was R2 and R1, and it's going to be negative R2 over R1 times our input voltage here. So, like you could go through and solve all this math, but what you're going to end up with is going to be V out equals 2 times negative 20 over 5 minus J2, because this is R2 over R1, right? Or Z2 over Z1. If we then do this math, we're going to get negative 40 over 5 minus J2 times 5 plus J2 over 5 plus J2. What does this turn into? Okay, 5 times 40 is 200, so it's negative 200 plus J80 over 5 squared plus 4 squared is 25 plus 4, which is 20, or 25, yeah, whatever, it's 29 there. I think, me fact check myself for V out. You get something. I'm not sure I did this right, but I have the answer right here in front of me, so I'm just going to fill in that eventually you get negative 7.42 e to the j 21.8 degrees. So yeah. So dot dot dot, you get this. And that would be in volts. So then for S of the load is going to be that equation we had earlier. So it's can either write it as 1/2 V I bar or 1/2 VI conjugate, or in the nicer, easier form for what we have here, we have this, right? Now we have all of these numbers. Wow. So we fill it in and we get 1/2 times 7.42 squared over, and then what is Z conjugate? Remember up here, it's given to us as 10 plus J5, so now it's just 10 minus J5. And if we plug this into our calculator or do the complex math, depending on what mood you're in, let's see, we got 7.42 squared. Shit, we messed it up. Okay, we got 0.5 times 7.42 squared over 10 minus 5i. And we end up getting, um, for our complex power, 2.46 e to the j 26.57 degrees. And this is the like volts amps reactive is the, or no, just volts amps is the unit there. Okay, so we have that. So we've done part one, right? We found the complex power. This is part of our this is part of our answer. And then the power factor, remember, is just the cosine of that. So is cosine of 26.57 degrees, which you can just do on your calculator and you get that.
I have a question.
Hmm.
For the power factor, usually is it not like cosine of phi of something minus cosine of it's
Yeah,
like cosine of phi something minus phi something?
yeah. So the reason this works is so remember what is it? I can give you a quick proof for this. So this is if we have our ZL and it has some voltage and some current going through it, right?
Mhm.
The power is one half V bar I bar, right? Or V bar I conjugate.
Yes,
If we think about this, I conjugate is going to so the V here will have some phase. So let's say this is AE to the J theta 1, and this is going to be sorry, okay, wait. Yeah, so let's say voltage is AE to the J, trying to just think about how to organize this on the page. Okay, let's say voltage is equal to AE to the J theta 1, and current is equal to AE to the, or say it's B E to the J theta 2, right?
yes,
I actually guess I should just call this phi V and phi I. Uh, Here, right, we take the conjugate of this, and that ends up being B E to the negative J phi I, right?
yes, yes.
So then when you multiply V bar times I bar conjugate, that's going to be AB E to the J phi V times E to the J phi I, right? And then based on
Negative phi
our,
I.
yeah, oh yeah, negative phi I. And then based on our exponent rules, you end up getting that. And so this here, because remember, this was originally our equation for S, right? You put in the one half
Yes.
there. So this is saying that that is equal to phi S. So that's why you can say
Oh,
that.
okay. I get it.
Yeah. Basically, it's it's the same thing. It's just two different ways to write it depending on what is easier for the question.
Okay, thank you.
No problem. Okay. Uh, I am out of time, so I will finish up now. Good luck on the quiz tomorrow. Practice your complex math, hopefully it's not too bad. All right. See ya.